Now, here it is the definition. Now, we will formally define the conditional probability. Suppose that we are interested in computing the probability of a event A, and we have been told given event B has occurred. The conditional probability of A given B is defined to be, let, so here we consider, let S be a sample space, let S be a sample space and C is a sigma field for any two events A, B. So, whenever it is event, then it is belongs to the sigma field C. The conditional probability of A given B is defined as probability of A given B, this is nothing but probability of A intersection B by probability of B, where here assume that probability B not equal to 0. So, if probability of B equal to 0, then we cannot define this conditional probability, it will be undefined. Similarly, the conditional probability of A given, conditional probability of A given B already we defined, conditional probability of B given A is defined as probability that B given A, which is nothing but probability of A intersection B by probability of A, where it is assumed that probability of A is not equal to 0. So, let us discuss some of the numerical example. So, what is the rationale behind it? So, if you are told that event B has occurred, then the sample space is restricted to B, like the example we discussed, whenever you are throwing a die, whenever it is informed that the even number occurred, then we need not to consider the sample space as 1, 2, 3, 4, 5, 6, because whenever we know the information that only even number are the possibilities now, the sample space now become only restricted to B, B is the even number 2, 4, 6. The probability within B has to be normalized, this is achieved by dividing by probability of B. So, here in this example, suppose this is the, in this graph we can see that this is the sample space, this is A and B. Whenever B observed, that means those sample points inside B, the possibilities now. Now, what is the proportion now that A out of B is the probability now for A given B, that is probability that A intersection B, that is the part by the probability of B. So, this is some as a to understand it, the event A can be now be occur if the outcome is in A intersection B, hence the new probability of A is probability A given B, it is probability of A intersection B by probability of B. So, let us do some numerical examples. Suppose here roll a balanced die once and record the number on the top space. So, what is balanced die? So, balanced die means we assume that all the faces are equally likely, probability that one of the observation may come, it is 1 by 6. Let E be the event that one shows on the top space. So, E is nothing but here 1, and let F be the event that the number on the top face is odd. So, F is 1, 3 and 5, these are the number of any of the number is odd. So, F is 1, 3, 5. So, from the classical approach, what is the probability E, because all are equally likely, their sample space S is here 1, 2, 3, 4, 5 and 6. So, probability of E will be 1 out of 6, 1 by 6, and probability of F, because it contains 3 equally likely points out of 6 equally likely points by classical approach. Possibility that number of way f can occur is 3 out of total number of way is 6. This is 1 by 2. Now this is the question. What are the question? What is probability of E? Already we have found it is 1 by 6. What is the probability of the event E if you are told that the number on the top face is odd? So now it is considered, so the question is that what is the probability of, what is the probability of E, what is the probability of the event E if we are told that the number on the top face is odd? If we are told that, if we are told that the number on the top face is odd, it's odd. So that means we have been given, so it is asked that find the probability of E given f. So now from the intuition we have discussed that, because whenever you have been given that number of top face is odd, now we are concentrated on, this is now the new sample space 1, 3 and 5, and out of these 3 only 1 happened. So this probability should be, from the institution it will be 1 by 3. Now we will apply the definition. So definition says that this probability is probability that E intersection f by probability of f. So now what is E intersection f? So probability of f we know it is 1 by 2. Now E intersection is f is nothing but each 1 intersection f 1, 3 and 5. Now 1 is a subset of 1, 3, 5. So only common point is nothing but 1. So this is nothing but E. So that's why this is nothing but probability of E by probability of f. So this is equal to probability of E is 1 by 6, probability of f is 1 by 2. So this is 1 by 3. So that we also from the intuition 1 out of 1 by 3 way it can come total 1 possibilities. So that is 1 by 3. So that is also, it is coming from the definition also. So this is consistent, this definition is consistent with our intuition what we understood. Now we will discuss this prisoner dilemma also. So prisoner dilemma, it is saying that A, B and C are in the jail and they are, one will be executed. So probability of that A will be executed 1 by 3 and A complement is 1 minus 1 by 3, that is 2 by 3. Probability that B will be executed, this is also probability 1 by 3. Probability of B complement is 2 by 3 and probability that C will be executed, this is 1 by 3. Probability of C bar will be 2 by 3, that we know. Now we have to find the conditional probability that, suppose guard says that B will not be executed, B complement. Now what is the conditional probability of A given B complement? So this probability will be probability that by definition A intersection B complement by probability of B complement. Now probability of B complement already it is known, this is 2 by 3. Now we have to understand what is A intersection B complement. Now what is B complement actually? B complement is B will not be executed. So B complement, it implies that, so in the sample space, so AC is nothing but, you can say that AC is nothing but A contain 3 points A, B and C. Now if B complement means, so if you can see that this is A, B and C, so B complement means just remaining A and C. So that means, so just I just want to explain it, but B complement is nothing but only the A and C can be executed. So that means A is itself a subset of B complement, hence A intersection B complement will be nothing but A. So that means this is nothing but probability of A by probability of B complement. So this is probability of A will be 1 by 3 by, or probability of B complement will be 2 by 3. This is nothing but 1 by 2. So that also we found. So, from the intuition that if it is informed that B will not be executed, then there are only two members A and C. Out of A and C, one will be executed. So, they are equally likely. So, 1 by 2, this probability 1 by 2. From the definition also we get that. But this is to understand very simple examples we discussed. So, more example we will discuss and also some more theorems also we will discuss. Now, what we found now? So, probability that A given B, it is nothing but probability of A intersection B by probability of B. If it is given that probability of B is not equal to 0, assuming that, which implies probability of A intersection B can be represented as probability of A given B into probability of B. Note that this notation is, it is not backslash or forward slash, this is just a vertical line A given B. Now, probability of B given A by definition, so this is conditional probability of B given A is by definition probability of A intersection B by probability of A, provided probability of A not equal to 0. From here we get that A intersection B is nothing but probability of B given A into probability of A. Hence, probability of A intersection B can be represented by two ways, A given into probability of B plus probability of B given A into probability of A. Sorry, not plus, this is equal to probability of A given B into probability of B plus probability of B given A into probability of A. So, this is one relationship. Okay. Now, next we will discuss. So, this is the solution already it is given and prisoner dilemma also. So, you see that the solution probability of E 1 by 6, A 1 by 2, E intersection is 1 by C. So, all these things we have discussed. So, you can go through these slides also, and here also prisoner dilemma probability of A equal to probability of B equal to probability of C 1 by 3, probability of B complement 2 by 3, A intersection B complement is nothing but probability of A, this is 1 by 3. So, probability of A given B complement become 1 by 2. So, those things are given in the slides also. Now, we will discuss one important concept, this is independence. Usually, how we understand independence? So, independence, there are many different contexts we talk about independence. Our Independence Day, so a country become independent. Sometimes we say that two variables are independent. So, whenever we say two variables are independent, some person is dependent on somebody like that. So, two variables are independent when we discuss like that x and y are suppose two variables, they are independent, that means they are functionally dependent, that means there is a function between y is equal to f of x, that means if you suppose this is equal to sin of x. So, if you x give a value 1, then y has to be some value, particular value sin of 1. So, there is no any other value. Suppose two friends, they go to market and buy some their expenditures. So, they decided that one friend actually following other friends. So, they decided that one friend whatever they will buy the items expenditure, suppose x is the expenditure, then the other friend will double their expenditure. So, his expenditure. So, then y will be, so if one friend expenditure is x, another friend expenditure is 2x. So, they are dependent, because if you one of the expenditure what is the in the market, if you know, then other value also you can know. So, this is known as the functionally dependent there. Now, in the context of probability theory, the independence is we say stochastically dependent. So, it is sense of some kind of probability. The probability of event is dependent of some probability of any other event or not. So, how we will define that? So, here it is defined in this way, two events. So, let here again we will discuss, let S be a sample space and C be a sigma field. It is a class of subsets of S. Two events, suppose A and B belongs to C, that means A is a subset of S and B also subset of S. are said to be independent if probability of A intersection B is nothing but probability of A into probability of B. So, this is called the two events are independent. So, from this definition, the terminology how I understand the independent, how it is understood here from the definition, how we can say that something like dependencies or independence, that means it is not dependent, some probability of A is not dependent on probability of B, something. So, how we can explain here? So, now just now we found that probability of what is conditional probability? Suppose A and B are independent, that means it satisfies this relationship. Probability of A intersection B is probability of A into probability of B. So, we will give some examples also. Now, we try to understand the definition first, that how this independence meaning actually associated with this definition. Now, let us find out the conditional probability. So, conditional probability of A given B. So, by definition it is nothing but A intersection B by probability of B, assuming that probability of B not equal to 0. So, now if A and B are independent, then probability of A intersection B can be represented as probability of A into probability of B by probability of B. So, then it will be cancelled, this is nothing but probability of A. Similarly, if you can find probability of B condition on A, so conditional probability of B given A, this is nothing but probability of A intersection B by probability of A, which is probability of A into probability of B by probability of A, assuming that probability of A not equal to 0, otherwise it will be undefined. So, this is nothing but probability of B. So, probability of A given conditional probability of A given B is nothing but probability of A. So, that means even if you are informed B is happened or you are not informed, this probability does not change. So, probability of A actually does not dependent on the B is happened or not. Similarly, here also you can see that if this condition satisfied, then probability of B given A is happened or not. So, this information is provided or not, it is not actually changing the probability of B. So, that means probability of A does not dependent on the conditional probability of A given B, it is same as the probability of A. So, probability of A does not change if you given this information B or not, or B is happened or not. So, that is why in this sense, in the probability sense, this A and B will be independent if these this condition satisfied. So, this is called the independence. So, this independence definition it is given here. So, you can see that two events A and B are called independent if probability of A intersection B is equal to probability of A into probability of B, that we just discussed now. So, now this is the explanation we just discussed. If PB not equal to 0 and PA not equal to 0, then probability of A given B is nothing but probability of A, and probability of B given A is equal to probability of B. Thus, in case of independence, the conditional probability of the event is not affected by the knowledge of the other event. So, in that sense, A and B are independent. Now, we have already discussed some of the concept. We say mutually exclusive. So, suppose two events mutually exclusive. Two events A and B are mutually if A intersection B are null set. And just now we learned that two events A and B are independent if probability of A intersection B is equal to probability of A into probability of B. Now, question is that sometimes whenever we learn the new topics, like we have learned mutually exclusive events, independent events, we have some kind of confusion or some kind of question is that whether one definition is equivalent to another definition or something implies others. Like we can have question like whether mutually exclusive and independence may be same, or if two events are mutually exclusive, then they are also independent, or if two events are independent, then they are mutually exclusive. So, this is the any of the relationships are there or they are not true. Okay. So, let us discuss some examples. Suppose if we A and A intersection B are A phi. So, suppose there is a sample space like this, A and B are mutually exclusive. So, this is A, this is B, and also probability of A not equal to 0 and probability of B not equal to 0. Now, as they are mutually exclusive, probability of A intersection B will be phi, probability of phi, this is equal to 0. Now, it cannot be possible that PA into PB, because both are non-zero. So, it can possible only when one of them has to be 0. In other way, if both are non-zero, if they are mutually exclusive, then they are highly dependent. That means, if one event happened, then another event cannot happen. Like two students going school like that, one if somebody come to the schools, then other does not come, like that. They are very much highly dependent. If one student if we found in this school, then we know that that other student will not be in this school, somewhere else. So, that is highly dependent. So, it will be independent only when one of them has to be 0, probability 0, then that is the only possibility that mutually exclusive implies independence, otherwise it does not imply they are highly dependent. So, what we found that in general mutually exclusive does not imply independence. So, we will also discuss that whether other way also true or not. Let us discuss one numerical example. So, here this numerical example, let us consider a random experiment of throwing a die. So, sample space is 1, 2, 3, 4 and 5. So, here the sample space S is nothing but, so let us consider the random experiment. So, we have given this example as a second example. The sample space, so this is rolling a die. The sample space, this is S2, contain 1, 2, 3, 4, 5 and 6, and we consider here it is a unbiased. So, this is a balanced die. Let us consider this event A is equal to 1 and B is equal to 246, 246, B is equal to 246 and C is equal to 36. So, these are the three events we consider. So, let us consider, we have did not denote B is equal to 246 and C is equal to 3 and 6. So, this is 1, B is equal to 246 and C is equal to 36. Now, let us consider this A and B. So, you can see that A intersection B, there is no common point, A contains 1 and B contains even numbers. So, this is phi. So, they are mutually exclusive. But what is probability of A? Probability of A is 1 by 6, probability of B 3 out of 6, this is nothing but 1 by 2, and probability of C is 2 out of 6. So, this is nothing but 1 by 3. So, what we found 1 by 3. So, probability of A intersection B, this is not probability of phi, this is 0, which is not equal to probability of A into probability of B. So, probability of A is also non-zero, probability of B also non-zero, this is 1 by 6 into 1 by 2, 1 by 12. So, this is not equal to 0. Hence, A and B are not independent. So, here one example that A intersection equal to phi mutually exclusive does not implies A and B are independent. So, just we can write that mutually exclusive does not imply independence. So this is one example. So in general, so it may be true for some of the events, like if one of the event A and B is 0, then it may be true that A intersection B phi implies A and B may be independent, but in general we found this example. Now next let us consider B and C. Suppose let us consider B and C. So what is B intersection C? See that B is nothing but 2, 4, 6 and C is 3 and 6. So this is given, B is 2, 4, 6 and C is 3 and 6. Now what is, sorry, not I wrote B intersection C, we consider B. B is 2, 4, 6 and C is 3 and 6. So what is B intersection C? B intersection C will be, see that the common point is 6 only. So hence probability of B intersection C will be, so let us write down here, probability of B intersection C, because it is only one point, by classical approach there are 6 total way of 6 samples it contains, and total way it can come 6 way, out of that B intersection C can come 1 way, so this is 1 by 6. So this can be represented by 1 by 2 into 3. So we can represent by 1 by 2 into 1 by 3, and so this is probability of B is 1 by 2 and probability of C is 1 by 3. So this is nothing but probability of B into probability of C. Probability of B is 1 by 2 and probability of C is 1 by 3. Hence, by definition, B and C are independent events. However, B intersection C not equal to phi. So they are not mutually exclusive. Hence, independence does not imply mutually exclusive in general. So that what we ask the question, whether one of the relation, so none of the relation correct. So there is no relation. So the two events may be mutually exclusive but may not be independent. Two events may be independent but they may not be mutually exclusive. So we have learned that what is the conditional probability, and how we can define two events are independents, and also the relation with mutually exclusive events and the independence. Next we will discuss one of the important theorem, it is known as Bayes theorem.